And when I saw the title of the meeting, I was attracted by this thin film. So I'll try to say something involving thin films, even though they have not been my main topic of research recently. This work this talk is based on a paper I wrote together with Valeria Chiodo-Piat on the sad occasion of the death of Vasily Zhikov, who was a Soviet mathematician, which was a very important figure in the theory of homogenization in Soviet Union and Russia, and was active from the 70s to some years ago. Okay, and he was interested 20 years ago. He was interested in homogenization on singular structures, in particular on networks. So we will look at a problem inspired by Zhikov on a three-dimensional network, on a part of the three-dimensional network. And we will come in the end to see that it has to do with some thin films. So it will have a kind of old-fashioned flavor, because it's based on work of a long time ago, if you want, but I hope it will make some connection with recent work. So the geometry I'm interested in is that of fast-oscillating, of sets with fast-oscillating boundaries. So we take a function, periodic function in the plane, G, which is the height function, and we scale it. Periodically, so the period gets smaller and smaller, but we don't scale the height. So the oscillations are higher and higher as epsilon tends to 0. A popular choice, you see a lot of papers involving this kind of geometries, where you have cylinders of fixed height, but of spacing epsilon. And you want to know what happens as this goes. Cylinder or cylindrical profiles, meaning that G takes only 2 values, say here. But we will see that it's not so different to consider general Gs. Okay, this kind of geometries I was interested in some 20 years ago. Actually, I think on a suggestion of Irene, when we were working on thin films. And so she pointed out a paper by Kohn and Vogelius, where they did something on equations, and then with Nadia Ansini, we were looking at the case of energies. So we are looking, so we have this subgraph. So we think that G is strictly positive, so that we have some spacing below, and then we normalize the maximum to 1. And we are looking at sets omega epsilon like this. So it's a notation. And we are looking at functions which are at energies which live on these sets. And we want to know what happens as this spacing goes to 0. So we want to have an approximate description. This is called a homogenization. And the way it is done by computing a gamma limit, which says that okay, they behave like, in average, say, like the gamma limit without the details that come from the complexity of the sets. So I give a brief recall of what we did. So the main point there is to understand what is the domain of the gamma limit. And so to do that, we define, we look at sections, look at sublevel sets. So we fix some height, Z, and we look at the sublevel set with fixed height here. And then we homogenize in reference energy, for example, gradient U to the P, because here we suppose that F grows like P, peak power, with P larger than 1. So we have this reference energy that we can homogenize in 2 dimensions. So this is a classical homogenization and gives some energy where Z acts as a parameter. Now this defines a stratified Sobolev space in a sense. So this phi will behave like gradient U to the P, or is gradient U to the P actually in the lower level because there is no microstructure, then it's more and more singular. And so it's defined, so this defines the behavior in the in-plane variables. And in the vertical variables, then you have, since you have fibers going up to the top, you have that the third variable is still integrable. Okay, the derivative in the third variable is still integrable. Okay, so the main point is the definition of stratified Sobolev space, and then the gamma limit is described by some homogenization formula in 3D. So we have something taking into account deformation of cubes, say, of 3D. Now we want to revisit this in a slightly different context, linked to what Zhikov was doing. Before doing that, I want to simplify a little the hypothesis, but this simplification will be indeed almost the general case in the case of networks. So we will look at G, which can be stratified, if you want. So meaning that we can find 2 points, two heights, Z1 and Z2, and below Z1, essentially the level sets are connected. So here, until we reach the first threshold, which we call T11 for some notation that we use after. Here it's just the whole, when you take the section, is the whole set. Then here it's a perforated set, but still connected. Here it's a slab, a perforated slab, but still a slab. And then here it's, when you take the section, is disconnected sets. Okay. So in this case, it's easy to, so the simplification is that we fix the directions in a sense. We take that the slab is in the x2 direction. So it's easy to define the stratified Sobolev space is the space which is W1P until this first threshold. Then you have, here you don't have any control on the derivatives of the first variable, so it's just the second derivative that is it's in LP, and here you only have some control on the third derivative. Okay, in general, sets, okay, if you take an arbitrary G, this will not have these properties, but it will can be decomposed in every level set can be decomposed by union of sets of this form. Here, there's some examples. Okay, but you can figure out. This doesn't satisfy this hypothesis, but when you take level sets, then you can write it as a union of sets of the form. Okay, or another remark is that usually function will have some of these sets which are empty. So in this case, in this case, either you have a connected set or you have completely disconnected set. And here, instead, you have either a connected set or a set connected in one direction. Okay. Now we go to networks. When we go to networks, we consider a portion of a network which lies below this oscillating graph. Okay. Here it is, and it's convenient to take also the backbone of what I call the backbone of the network, where we remove all the horizontal, unnecessary, parts, all the segments which are not all below the graph. And note that the set that we consider is not. If we scale by epsilon, we don't obtain the same set by the scale, but we have different sets depending on epsilon. But just stay below the same oscillating graph. Okay. Then we take. We have to define something. As before, we had this sigma z. Now we have this S of z, which is the underlying square network. So we take the section and we take the part of the square network on the basis without the segments which are not completely contained in the domain. And we suppose that S of Z then satisfies the analog of the assumption that we had seen before. Just here, we suppose that, okay, between Z1 and Z2, so the connected components in the Z2 direction are contained exactly in the slice 0K, where K is the period times R. Now we have to introduce another period which must be a multiple of the spacing of the lattice. So in this dimension, we suppose that G is periodic of some period, integer period K. Otherwise, we have some incommensurability problems. Okay. So we suppose that we can just look at slabs or just look at the reference cell, and everything happens in these slabs. This is not great. It just simplifies the formulas. And then we look at energies. Now here, tonight I noticed that I oversimplified this slide because I have to confess this, probably nobody would have noticed this, but I took, for simplification, I took the scalar case. Okay, and then I underline that I take this convex hypothesis, which in the scalar case usually it's not a big deal. But indeed, okay, I don't want to put back all the vector valued case that I had erased. So think that we use the fact that the function is convex, and we don't use the fact that the variable is scalar. Okay, so the way we use the convexity is independent of the fact that the variable is scalar. So this is for technical, I will need convexity, yes. Even if I were in the vectoric case. Okay, if I'm in the scalar, I don't need it because I can relax, but okay. I don't want to use relaxation. So these are the hypotheses. And this is the energy. So I take this one-dimensional network. I take these energies which are periodic in all directions. So they are cellular, if you want, energies. And these are defined on C1 functions so that everything is well defined. And so this is well defined, even though you take into account only what happens to you on the network. And we have to scale it. Okay, the number for a unit cube, we have 1 over epsilon squared vertical lines of length 1. So we have to multiply by epsilon squared to keep it of order 1. Okay. What I first use as a simplification is that instead of taking the whole network, I just can take the backbone. What is left out can be minimized separately. So you just minimize what happens on each segment, and this gives you a constant. So to fix this constant equal to 0, we suppose that that the energy is 0 when the gradient is 0. So you just take a constant on this slab. So the gamma limit then is the same. So we can restrict to the backbone, which has a nicer geometry because it takes it is just determined by the projection on Z2. Okay, and so we have to define a convergence. So there are many ways to define a convergence from the network to the continuum. Take into account that the network is oscillating, but it's periodically oscillating. One way is take the H1 measure restricted to this backbone, and then take notice that this converges to a constant depending on the third variable, actually this constant here, well, a function depending on the third variable times the Lebesgue measure. And we can define the convergence of sequence U epsilon of C1 functions, but they are just defined on the network to U, if we have these measures with coefficients U epsilon converge to U times the limit measure. Okay, and this is a compact convergence, meaning that it's compact on sequences with bounded energy. And the idea here actually is that you have a first layer in which you have classical compactness, if you want, compactness on full-dimensional networks, and then you inherit the compactness in the vertical direction using that you have these fibers in the vertical direction. Somehow it's what already was used in a paper with Irene and Gilles Francfort long ago for thin films. Okay, but you can define the limit, and the limit is in the space that we had described before, which is the third derivative is in LP, and the other two are in LP of the proper spaces. Now we want to reduce to periodic networks. So somehow this is a complex problem which depends on X3, and we want to characterize the limit in a simpler way. So before we had not, we said that there is a three-dimensional local formula. Now we want to describe the limit better. And so for networks, we make a trivial remark that since on the basis we have k-square points, the number of configuration is finite. So you have only a finite number of changes of type, so you can find a finite number of points. So this is the profile of G, say, so that the network changes type. Okay. So here I introduced until from 0, Z1, here there is one point in which the network changes from a complete network to a perforated network. Then here there are two types of network which are coercive, say in the X2 direction. One is just as a slab, the other one is a perforated slab, and so on. Okay. And we note that if we limit to one of these horizontal sets, now our network is just the trace of a periodic network on all R3. And we call this network Sij. I runs from 1 to 3, and J is the subdivision of these three vertical segments. So this is a network which is the analog of a full-dimensional domain, or with some perforation, if you want, in this region. This is a periodical layer of thin films, and here it's just a periodic array of rods of different types when you are in different segments here, but you can just look at what happens. So you can extend it to an infinite network with the same properties. So we look at what happens in the three cases. So we either have a perforated or full-dimensional network, and here this actually had been already studied in a much more general setting of p-connected measures by myself and Valeria Chiudo-Piat, and essentially you can pass to the limit with this convergence and you obtain a full-dimensional, three-dimensional homogenization. And this three-dimensional homogenization in this particular convex case is described by a single self-problem formula. So you take a cube and you apply periodic boundary conditions plus a fixed strain, and you optimize. So this is a classical periodicity formula. If we are in the second case, so when you have a periodical array of thin films, we are in a situation that in the bulk we can imagine like this. Indeed, every one of these we can imagine that inside every one of these labs you have a network which is essentially in the x2 direction, but can be very wiggly, like something like this one. So it's not exactly in the geometry that has been treated by myself, Irene, and Gilles Franfort way back in 2000, or by Alejandro Cicalese and myself for thin films, for discrete thin films, but you can prove all the same that you can homogenize this. So these kind of thin films. The main point here is that you are taking something which is defined in all these three-dimensional set, but then the limit is just so it depends only on the derivative in the vertical and then x2 direction, but it's given by this formula, which is exactly the formula for a single thin film. So it's not a three-dimensional formula, but it's a thin film reduction. So this is finally the connection with the theory of thin films. And this is due essentially by the convexity. So we'll come back to this. What about the thin rods? Well, it's exactly the same story. So we now are looking at the third type of networks, which are composed of disconnected sets times Z2, say if you want, time R, and here what you obtain is just something depending on the third variable, and the formula is exactly the one you prove for thin rods. So again, in principle, you have to optimize oscillation on all the rods, but you just have to take a single one. Okay. So you can sum up all these results, which in principle hold separately on the different slabs. So on the different between Tij and I minus 1 j, maybe I and j were differently used before, but okay, in one of these connections you have a well-defined formula, but okay, you have some transition from one to the other. Well, this transition is negligible. So this theorem says that you can just pile up the constructions, and if you define this homogenization formula, stratified homogenization formula, then you get that the limit is defined of this form. Okay, it's defined in the whole slab, and it becomes more and more singular as x3 increases. Okay, and now you have to understand what is the gradient. Essentially, it's the absolutely continuous part of the gradient. Of course, it can be just a distribution. So, okay, if you want to be precise, here you have to be a little picky. But essentially, it's the absolutely continuous part of the gradient. Okay, so this is the this is the result. And what does it tell, this result? Well, it tells that, okay, first I said that usually people look at cylindrical sets, and this seems a high simplification. Well, it is not, actually, because locally you can always reduce to be close at least, and then by approximation to be on a cylindrical set. This is a general remark, not only for network. And conversely, there is no reason to use only cylindrical set, because with little effort you can use any profile. So somehow, if you have more complex profile, you just use this say principle to localize it in the vertical direction. So the theorem, of course, the lower bound it's immediate, because you can localize on each stripe and look what happens there, and then the single theorem says that in each stripe the thing objects behave in a collective way, and this allows to construct recovery sequences. Okay, this is allowed by the convexity. So the convexity allows that this reduction through thin film, which is very simple if you want. You are looking at a collective behavior of, if you want, a bunch of rods. Then you take the average behavior, and then by convexity you construct a sequence which gives an upper bound by the average behavior. There is also another improvement, that we use a weaker convergence, for which we have compactness. In the previous paper, actually, this was not needed because the application was on thin film, where you get some more compactness due to the rigidity in the third direction. Okay. So I have another 10 pages of concluding remarks. No, just two, okay. Actually, the fact of having networks here was just a suggestion to use thin films. When we understand that we can use thin film, we can reread or rewrite, if you want, our previous theorem, the classical theorem, in terms of thin films. So that you stratify, and then you take the level sets, you take the cylindrical sets with section the level sets. You take the thin film limit or thin rod limit of these sets, and then you describe the homogenization. This was for convex energies. Okay, we left open. We didn't think much about what happens when you have non-convexity. Maybe you have to convexify one more, so maybe quasi-convexify. So I don't know. There is some technical point there that may be of interest. And well, we have used networks, but indeed we have just used something which is called the p-connectedness of the network, which is a kind of validity of a Poincaré formula, which says, the fact that if you have gradient 0 on a network, then you have, or small gradient, then you're close to a constant, say. And it may be generalized to other singular measure, but the important thing here was that p-connecteds were inherited by the sections. So the measures must be such that you have to, this p-connectedness must be inherited by passing to lower dimension. And this can be, of course, extended to arbitrary dimension, but then it's more messy to state it. Or we can think of extending to brittle fracture, so that here brittle fracture will give you some effective energy, which is in general crystalline. So just to have also the other keyword of the conference inside the talk, and maybe this can be then again this principle of reducing to a single thin film limit can be stated also in this framework, but fracture energies are non-convex, so this is not clear. If we can go to brittle thin films, another thing that we looked at with Irene. And then you can think of oscillating boundaries which are with a random dependence which have been studied recently, and the relation with the random thin objects, random thin films, and so on. So maybe there is something in this little problem that we can look up. Thank you for your attention.